We're going to talk about the types of energy. So there are 4 types of energy you need to be familiar with in this unit. The first one is dissipated energy. There are several names for dissipated energy. We can also call it internal energy or thermal energy. And this is energy due to the motion of atoms in a material, and it's related to the temperature. The time that we will be using dissipated energy the most is when there's friction involved, because friction between two surfaces, kinetic friction between two surfaces sliding together, will result in those surfaces heating up a little bit, and that dissipates energy. So it increases the internal energy or the thermal energy of the materials. Next is gravitational potential energy. This is energy due to an object's location in a gravitational field. So if we take something and we raise it up in the gravitational field, it will have more gravitational potential energy. If it has more mass, it'll have more gravitational potential energy. Kinetic energy is the energy due to an object's motion. So the center of mass of the object is moving. And then spring potential energy, which is also called elastic potential energy, is energy due to the deformation of an object with a restoring force. So a rubber band is stretched, a spring is compressed, a bouncy ball compresses, and it has a restoring force, so it wants to spring back into its natural shape. And so that stores energy. To keep track of energy, we're going to use energy bar charts. So we call these LOL diagrams for short, because we have a bar chart, and then the circle in the middle shows you the system. So that's where you're going to list all the things that are in your system. Remember, it's important to establish a system because there's energy everywhere. There's tons of energy in the universe that exists in lots of different places. And we want to draw a line around a system and just say, I'm only going to worry about this energy here. And then we draw an LO or a bar chart for our final situation. So we're just listing the types of energy involved in the situation along the bottom axis of those bar charts. And this is a quantitative activity, or qualitative activity usually. So you do not have to worry about exact numbers of bars, like you could choose 2 or 3, it doesn't really matter. What does matter is that we have to have the same number of blocks in the initial situation as the final situation, because energy is conserved. And then from that, we can write our energy equation. So let's do an example. Here we have a bungee jumper, and the bungee jumper is jumping off of this platform up here, and we're going to draw an LOL diagram for situations 1 and 2 of the bungee jumper's fall. So the first thing we need to do is establish the system. So we're going to put the person in the system. We're also going to put the earth in the system. In order to have gravitational potential energy, you have to include the earth, because that energy is stored within the gravitational field interaction. And then we also want the cord, the bungee cord, in the system. Now also, when we're doing gravitational potential energy, you have to set a 0 reference line. I think that didn't go quite where I wanted it to go, so I'm going to do that one more time. And this is just the place where the gravitational potential energy is 0. And we call that a 0 reference line. So UG equals 0 at this point. And that's usually established at the lowest position of the object. And the reason that we need to establish it there is just to make our math easier. There's gravitational potential energy. If you think about something on the ground, you might say it has no gravitational potential energy, but then just imagine like a whole collapsed, like the floor collapsed into a cave. Well, then it would speed up and fall, and so that gravitational potential energy is turning into kinetic energy. So we're just setting a 0 reference line, the lowest position of the object. Okay, so now we think about the energy that we have in situation 1. So in situation 1, there's some gravitational potential energy and there's some kinetic energy. And then in situation 2, there is no kinetic, because we can see that the person's not moving. That arrow is a dot. There's no gravitational because they're at the 0 reference line, but this bungee is stretched, so there's spring potential. I'm going to say that there's 2 blocks of gravitational and 2 blocks of kinetic in the beginning, and in the end we have 4 blocks of spring. Like I said, the number of blocks doesn't really matter. What matters is that you have the same number in the beginning as you do in the end. So now we can write our equation: gravitational potential energy at 1 plus kinetic energy at 1 equals spring potential energy at 2. And that's all we do. And eventually we'll learn equations, we'll derive them in the lab for each of these types of energy, and then we can plug those in and solve for things that we don't know. But for now, that's where you're stopping. Let's do another example. So here we have a rocket ship and it is taking off. So in our system, we are going to put the rocket and the Earth. And I'm going to go ahead and put the fuel in there just to help us out a little bit. And then this is going to be the same. Your system is going to be the same, so you can just put little quotation marks over here. And in the beginning, we are not moving. We don't have any, we need to set a 0 reference line. We'll set our 0 reference line here. We don't have any gravitational potential energy, so we just have chemical potential energy. I know that I didn't put that as one of our options, and the reason I didn't is because we don't use it a whole lot. We won't have an equation for it, but that's chemical potential energy. So as the rocket is launching, the chemical potential energy is going to go down, and the gravitational potential energy goes up, and the kinetic energy goes up. And then here we get even higher, and it goes even faster. So I kind of ran out of gravitational potential or chemical potential. I might add one more block over there so that I still have one left. So chemical potential energy, there's one left, and then we've got 2 gravitational and 2 kinetic. And so now I can see I have 5 blocks the entire time. My chemical potential energy is going down, and my gravitational potential energy is going up. My kinetic energy is going up. So then I can write my first law of thermodynamics equation, which is just that energy is conserved. So UChem1 equals UChem2 plus UG2 plus K2, which is equal to UChem3 plus UG3 plus K3. All right, there's the second example. Let's do one more. This is a person bouncing on a trampoline, and we are going to do all of these points. So in the system, we're going to put the person, we're going to put the trampoline, and we're going to put the Earth. So in the system, when you're establishing your system, you need to put everything that could store energy and everything that could be moving, basically. I'm going to set my 0 reference line at the lowest point for the person, and we're going to have the same system the whole time. So at situation 1, the person has just elastic potential energy. They're not moving, which is what that dot is for. So I'm going to say spring potential energy, and I'm going to give it 4 blocks. Then at position 2, now the trampoline is not stretched anymore, and so we just have no elastic potential energy, no spring potential energy. The person is moving pretty fast, and they're a tiny bit above the 0 reference line, but not very far. So I'm going to give them 1 gravitational and 3 kinetic. And then at position 3, now we're slowing down quite a bit. We've got a bit higher, so I might give them 2 gravitational and 2 kinetic. And then at situation 4, now they're stopped to turn around, denoted by that dot there. So we have all gravitational. So we can see as time goes on, my spring only existed in the beginning. So my gravitational, as the person's going up, is going up, and then my kinetic is going down as they slow down. So then I can write my first law of thermodynamics equation, US1 equals UG1 plus K1. Ooh, goodness, that's supposed to be a 2. which is equal to UG3 plus K3, which is equal to UG4. And that is our example there.